In this video, we're going to talk about LHpitals Rule. LHpitals Rule is the last bit of chapter 6 for us to talk about together. And what I want to do is I want to first introduce you to the idea of indeterminate forms. So indeterminate. So indeterminate forms are certain quantities that you can't just look at and know what the answer is. So for example, if you were to look at something that's of the form 0 over 0, it's tempting to call that 1, but it turns out that you can cook up examples of limits that are of the form 0 over 0, where they turn out to be whatever you want. So for example, if you were to look at, just to make this as easy as it can be, if you were to look at the limit of, say, 4x over 5x as x approaches 0, now 4x goes to 0 as x goes to 0, 5x goes to 0 as x goes to 0, and yet the ratio is not, I mean, it's of the form 0 over 0, but the ratio is 4/5. And of course, you can think of numbers that make this value to be whatever you want. You could actually make numbers where this limit doesn't exist, where this limit is plus or minus infinity. So for example, if you had, I'm trying to think of what a good example here would be, but if you were to have something like the limit of, say, x squared over 7x as x goes to 0, that's 0 over 0. The x's cancel, and this is 0. If you were to have 7x over x squared, that limit wouldn't exist because the limit from the right and the left go to plus or minus infinity respectively, and those aren't equal. So the limit doesn't exist. You could have limits where the value goes to plus infinity or minus infinity. Basically, you can make 0 over 0 do whatever you want. And so that's what we mean when we say it's indeterminate, is that it's not determined by this value. You can make it equal to whatever you want it to equal, okay? Or to say it a slightly better way, not that you can make it whatever you want it, but there are quantities of the form 0 over 0 that are equal to whatever quantity you can think of. So again, whatever real number you can think of, 0, infinity, pi, 4/5, negative infinity, negative 107, whatever you want it to be, you can come up with examples that are 0 over 0 that equal whatever you want them to be. So that's what we mean when we say an indeterminate form, okay? Something that doesn't have a fixed value. A few other indeterminate forms include infinity over infinity. Okay, so, and it doesn't matter the sign, whether it's plus or minus infinity over infinity. So again, you can make values that are infinity over infinity equal to whatever you want. Okay, you can come up with examples of this form that equal whatever value. It could be 4/5, it could be infinity, it could be 7, again, whatever. A few other surprising indeterminate forms. Okay, so there's infinity times 0. Okay, so if you have infinity times 0, it seems on the one hand that if you were to have infinity times anything, that should be infinity. And yet that's fighting against the impulse that if you have 0 times anything, that should be 0. And so those sometimes can fight against each other, and you have to figure out which one wins. And so sometimes these limits can be 0, sometimes they can be infinity, sometimes they can be 7, they can be whatever number you want. Again, these are indeterminate forms, so just knowing this is not enough. 1 to the infinity, okay, that's another indeterminate form. So if you were to have 1 to the infinity, that's not well defined. And there's a few others. Infinity minus infinity, that's an indeterminate form that you can kind of think of that. That's very similar to the 0 times infinity. So that's along the same vein. And then there's a few others that we'll talk about as we go along. Okay. It turns out that, I guess I might as well say, if you have infinity to the 0, okay, that's also an indeterminate form. Okay, that can also be whatever you want it to be. Or you can, when I say that, what I mean is you can cook up examples that are of that form that turn out to have whatever limit you want them to have. So infinity to the 0. And then one that I want to just point out that gets overlooked a lot. So let's talk about things that are not indeterminate forms. I ran out of room here, so I'm just reorganizing. Okay. There might be one more indeterminate form that I missed, but the following are not indeterminate. And so if you see quantities that are like this, okay, so not indeterminate, this includes 0 to the infinity. 0 to the infinity is just 0. because the inside is small, it's less than 1, and you're raising it to a higher and higher power, that's just going to go to 0. So infinity to the 0 to the infinity is going to approach 0. So if you have any limit like that. Infinity plus infinity, okay, is going to be infinity. So this is like the idea if you have two large numbers and you add them together, you get another large number. Infinity times infinity. Okay, that's also going to be infinity. Okay, so if you have two large numbers and you multiply them, you get an even larger number. Okay, so these are all examples of forms that are not indeterminate. Okay, but really L'Hopital's rule is a rule that's going to allow us to look at indeterminate forms. And to be honest, we can actually get away with studying basically these first two types. Okay, 0 over 0 and infinity over infinity. We don't need to worry too much about the others, and I'll explain why as we go along. Okay, but what I want to do is I want to talk about how do we handle limits of the form 0 over 0 or infinity over infinity. And I actually want to point out that you've been dealing with limits of the form 0 over 0 your entire calculus life. Because when you talk about derivatives, remember what a derivative is. The derivative is just the limit definition of a derivative. It's the limit of f of a plus h minus f of a over h. It's a difference quotient as that difference goes to 0. So a plus h minus a is h, and h itself go to 0. And so as h goes to 0, you get 0 over 0. And we've been playing with derivatives our entire calculus career. Okay, so the 0 over 0 idea is something that should be familiar to us. And infinity over infinity is pretty closely related, I mean, okay, not far behind. So let's state L'Hopital's rule. And then what I want to do is I want to do a few examples. And I think I'm going to break this up into a few videos because there's a little bit of theory that I want to get into here as well. So L'Hopital's rule says the following. Okay, so L'Hopital's rule says that if you have a limit, so I'm going to write it like this. If you have a limit as x approaches p of f over g, so you're looking at a ratio of functions. And if this limit is of the form, I don't want to say equals, but is of the form 0 over 0 or infinity over infinity, I don't care if it's plus or minus with the infinities, then the limit of f over g as x approaches p is equal to the limit of f prime over g prime as x approaches p. Okay, there's a few things I want to point out right away. The first is that p can be any real number that you want, or this also works if p is infinity or minus infinity. Okay, so the same thing is true if p is infinity or minus infinity. The second thing I want to point out is that when we differentiate f and g, we are not differentiating the quotient. We do not use the quotient rule. We're differentiating the numerator and the denominator separately. Okay, and that's very important. We are not taking the derivative of the quotient. We just differentiate the numerator, and then we differentiate the denominator, and then we put them in the numerator and denominator. Okay, and so this is L'Hopital's rule. L'Hopital's rule was discovered by not L'Hopital. L'Hopital turned out was just a rich guy that learned about, he was a student of Bernoulli. Bernoulli was one of the, he was a contemporary of Isaac Newton. I don't want to say friends because I don't know if they were friends, but he was around the same time as Isaac Newton. And Bernoulli did a lot of discovery of mathematics. So there's a lot of Bernoulli stuff floating around. So Bernoulli's a name that you've probably heard of or probably have come across, even if you don't remember it. Anyways, L'Hopital was basically he was a rich guy that really liked math and was a student of Bernoulli and learned about this rule. And then he wrote his own calculus book, L'Hopital did. And I think L'Hopital was maybe the first one to write this rule down. So it's kind of got attached to his name, but it's not really his result. Anyways, so this is L'Hopital's rule. I don't want to get too much into the proof of, why this works to T, but I want to just mention a few things. L'Hopital's rule is really just an extension of the mean value theorem. Okay, and so the mean value theorem is a result from section 3.2 in our book, and I just want to remind you of what this says. So the mean value theorem says that if you have a function f, and if f is continuous over some closed interval, by closed I mean an interval with endpoints. So if f is continuous on some interval and differentiable in the open interval, by open I mean the interval without endpoints, then there exists a value c. So then there exists a value c where the derivative at c is equal to the mean value of the function, or the average value of the function over that interval. So it's equal to that difference quotient. Okay, so f prime of c is equal to f of b minus f of a over b minus a. And so this is the mean value. This is the slope of the secant line. So if you were to have a graph here of a function, so let's say you have f looks like this from a to b, so it's going to be continuous over the interval with endpoints, differentiable on the interval without endpoints, right? There's no making sense of the derivative at that point if you can't continue it. But what this says is that if you were to look at this quantity, this f of b minus f of a over b minus a, that's going to be the slope of the secant line. Okay, so the secant line is the line connecting those 2 points. Okay, and so what this says is that there's got to be a point in between. I forgot to actually add one thing here. So then there exists a value c in the interval from a to b where the derivative is equal to the mean value. So what this means is that there's a value in between a and b, and just by looking at the graph, it looks like the value is about here, and also there's another value here. But if you were to compute the derivative at that point, it would be the same as the slope of the secant line, because the tangent line and the secant line would be parallel, right? So the slopes would be equal. So that's the mean value theorem. And the mean value theorem is useful here because it turns out what you can do. So I'm just going to kind of give you a preview of what this looks like. But it turns out what you can do is you can write f of b minus f of a as f prime of c times b minus a. And so basically what you're allowed to do here is if you apply the mean value theorem cleverly, you can rewrite this function f and g as, if we, let's say we add this f of a to both sides. Let me just write what I want. F of x is going to be f prime of c times x minus a plus f of a. So I'm letting b be x, and I'm thinking of this now in kind of a functional form. And so what you can do is you can do this for f and for g. And if you do this cleverly enough, then you can choose f of a and g of a to be 0. Because remember, this works for any interval. So anyway, so you can do this, and you can basically exchange f of x for this expression. And you have a similar expression for g, right? So for g, you get that this is going to be equal to g prime of c times x minus a plus g of a. And so if you do this cleverly, you can get the f of a and g of a terms not to matter. And then looking at f over g is really just looking at f prime times x minus a over g prime times x minus a, and the x minus a's cancel, right? Again, if you're clever enough and can get these terms to go away. So that's essentially what LHpitals rule is and how it follows from the mean value theorem. It's really just an extension of the mean value theorem. By extension, I mean it's an application of the mean value theorem. Okay, and so that's kind of the theory behind this. But let's also talk about how this is going to work in practice. Okay, so in practice, we're going to see a few limits. And so let's evaluate the following limits. Okay, so I want to evaluate the following limits. So the first is, let's evaluate the limit as x approaches 1 of x to the 5th minus 1 over x squared minus 1. Now, one of the things that's super critical here with LHpitals rule is we have to make sure that the hypotheses apply. if we have a limit and it's not of the form 0 over 0, then or infinity over infinity, then we can't use L'Hopital's rule. We just have to come up with some other method to evaluate this. Okay, this only works for the special limits that are of the form 0 over 0 or infinity over infinity. That's it. Now, if we plug in 1 for the numerator and denominator, we get 0 over 0, and then we can use L'Hopital's rule. Everything is fine. So what we're going to get here is if we take the derivative of x to the 5th minus 1, we got 5x to the 4th. And if we take the derivative of x squared minus 1, we get 2x. And this is going to turn out to be 5 halves times x cubed. And as x approaches 1, we get that this is 5 halves. Okay, because we're plugging in x equals 1. So notice that we could only apply L'Hopital's rule once here, because as soon as we apply it once, we get a non-zero in the denominator in the numerator. Okay, but when we plug in 1, we're done. We got 5 halves, and that's it. That's how L'Hopital's rule works. So it's a really nice, neat way to evaluate these limits. All right, let's look at the limit as x approaches 0 of e to the 2x minus 1 over sine of x. And we want to look at what happens as x approaches 0. Again, as x goes to 0, e to the 0 is 1. So e to the 2x minus 1 will be 0 when x is 0. And likewise, sine of 0 is 0. So L'Hopital's rule applies, and we get that this is the limit of, we're going to get the derivative of the top. So that's the derivative of e to the 2x minus 1. So it's going to be 2 e to the 2x, all over the derivative of sine of x, which is cosine of x, of course. And now when x approaches 0, we just get a value that we can plug in. We get 2 times 1 over 1, which is just 2. And that's it. Okay, this is a limit. So this top one you could have factored, right? You have a difference of powers. There's a rule for that. You can figure out how that works. No, x to the 5th minus 1, it's not the most pleasant algebra, but it's not terrible. X to the 5th minus 1 is x minus 1 times x to the 4th plus x cubed plus x squared plus x plus 1. Because that's how differences of powers work. And the same with x squared minus 1, right? This is x minus 1 times x plus 1. And then when you plug in x equals 1, you get 5 over 2. So you could have done this one algebraically, although it would have been kind of a pain. This one, though, you can't do algebraically. There's just no nice way to do that, at least without some kind of clever, some clever algebra. You could conceivably, what you could do is you could think about the limit definition of e to the x, but then you have to, there's a lot of thinking that's involved there. So this is one that by far the easiest way to do it is L'Hopital's rule. Okay. Let's look at the limit as x goes to infinity of x times sine of pi over x. Now, at first glance, this is not 0 over 0 or infinity over infinity, but it's infinity. As x goes to infinity, x goes to infinity. And as x goes to infinity, sine of pi over x, well, pi over x goes to 0, sine of 0 is 0. So this is infinity times 0, right? You have infinity times 0. And that's indeterminate. And so we have to think about how can we turn this into something that is going to be a little bit easier to work with. And it turns out the right way to do that is to rewrite this algebraically. And this is going to be the limit as x goes to infinity of sine of pi over x divided by 1 over x. So instead of multiplying by x, I'm dividing by 1 over x. And now we have 0 over 0. Now we can do L'Hopital's rule and everything is fine. So this is going to be the limit as x goes to infinity. And we're going to differentiate sine of pi over x. That'll give us cosine of pi over x times the derivative of pi over x, which will be negative pi over x squared. And then we're going to divide by the derivative of 1 over x. So that's negative 1 over x squared. And lo and behold, the negative 1 over x squareds are going to cancel. So what I mean by that is that the negative 1 over x squared here and the negative 1 over x squared is going to cancel there. Okay, so those are gone. And this is just going to be the limit as x approaches infinity of cosine of pi over x times pi. And that's perfectly well defined. Cosine, so pi over x still goes to 0. Cosine of 0 is 1. So altogether, this is going to be 1 times pi, or just pi. So it turns out that's what the limit's going to be there. Okay, so that's the limit as x goes to infinity. A few more examples here. Let's look at the limit as x approaches 0 of x squared sine of x over sine of x minus x. And this is 0 over 0. And so LHpitals rule applies. And let's see what happens. If we differentiate the top, we need the product rule. So no big deal there. But if we differentiate the top, we're going to get the derivative of the first times the second plus the derivative of the second times the first. So it's 2x sine x plus x squared cosine x all over the derivative of the denominator, which is going to be cosine of x minus 1. Okay, and now when we plug in x equals 0, we get 0 over 0 again. Okay, so not obvious that we've made progress, but we can try LHpitals rule again. So here we're going to take again the derivative of the top over the derivative of the bottom. Derivative of the bottom is a little easier, so we'll do that one first. And then for the derivative of the top, we need the product rule twice because we have 2x sine x plus x squared cosine x. So no big deal, we'll just do the product rule twice. So for the first one, I'm going to factor out the 2. And then I'm going to look at x times sine of x and apply the product rule there. So we're going to get the derivative of x times sine of x plus x times the derivative of sine of x. So that's fine. So 2 sine of x plus x cosine of x. And then for the derivative of x squared cosine x, we do the straightforward product rule. So we get the derivative of the first times the second plus the derivative of the second times the first. So it's minus sine of x times x squared. And then I just want to simplify the algebra just a second here. This is the limit as x goes to 0 of 2 sine x plus, here we have 2x cosine x plus 2x cosine x is altogether 4x cosine x. And then minus x squared sine of x. And that's all over minus sine of x. Okay. And there's a little bit of simplifying that we can do here for now if we want to. So if you want to, I think a little algebra will go a long way. But we're going to take the limit as x goes to 0. We're going to have 2 sine x over negative sine x plus 4x cosine x over negative sine x. And then plus x squared sine x over sine x. The negatives there canceling each other. So we had a negative here and a negative there. Okay, so those cancel each other, everything's fine. Now, the reason for doing this is that here the sine of x terms are going to cancel. We get just negative 2. So we're going to get negative 2 plus, we'll still have to take the limit of the middle one, but we can rewrite it a little bit if we want. We have negative 4 cosine of x times x over sine of x plus the last expression, the sine of x terms cancel. And so then we're left with x squared, the limit of which as x goes to 0 is 0. So all we really have to do is look at the limit of the following, the middle term there, okay, that final term. And negative 4 cosine of x is going to go to negative 4. So all we really have to know is what happens to x over sine of x. And you can either remember from Calc 1 that this limit is 1, or so this gives us a final answer of negative 6. Or if you want, there's nothing wrong with doing LHpitals rule one last time. And let's just do it with the whole expression. We had 4x cosine x over negative sine x as x approaches 0. And just applying L'Hopital's rule, because this is again 0 over 0, you get the limit as x approaches 0. I'm going to factor out the 4 from the top when we differentiate. We're going to get the derivative of the first times the second plus the derivative of the second times the first. And that's all over the derivative of negative sine of x, which is negative cosine of x. And now we're at a point where we can no longer keep applying L'Hopital's rule because we don't have 0 over 0 anymore, which is good. We have negative 4. Because here's a 4. When we plug in x equals 0, we get 1 minus 0. So this is a 4 up top, and then a negative 1 down below. So we got negative 4 altogether. And again, if you recognize that pattern that the limit of sine x over x or x over sine x is 1 as x approaches 0. So this is what I used. I'm going to call it theta just so it's not confused with what we have here. Okay, but that limit's 1. This is something that you learn in section 2.3 in Calc 1, maybe 2.4. Yeah, 2.4. But anyways, you learn it in Calc 1. When you talk about the derivative of sine, this is a limit that you have to deal with. And so we evaluate this limit by doing some trig and applying the squeeze theorem. But either way, you can apply L'Hopital's rule if you want, or just remember that limit. You're going to get negative 6 for our answer. So our final answer here is going to be negative 6. Okay, and so that's the last thing I need to say about that example. One more example that I want to do, and this is going to be one that's going to be very important for us, is I want to look at the limit as x to the x. Now, I don't mean that this specific limit is important to us, but this idea of how to evaluate the limit is going to be very important. And I think 0 to the 0 is the indeterminate form that I forgot before. I think there's 7, if I remember correctly. I don't really care about listing all of them, but yeah, but I forgot 0 to the 0. That's also an indeterminate form. Okay, and so here we have 0 to the 0, which is indeterminate. And what we're going to do is we're going to do a little trick here. And the trick involves calling this limit L. And then what we're going to do is we're going to compute not L, but the natural log of L. So the natural log of L is going to be the natural log of the limit as x approaches 0 of x to the x. Here we're approaching 0 from the right because if you have negative values of x, this isn't well defined. And because the natural log is continuous, and we've always done this trick in reverse, but it turns out that it's helpful the other way this time, we can move the natural log in and out of the limit. Here we want to move it in the limit. So this is going to be the limit as x approaches 0 from the right of the natural log of x to the x. And the reason why we want to do that is that now we can take our x down in front. So we can take our exponent and move that down in front. So this is the limit as x approaches 0 of x times the natural log of x. And this is, again, indeterminate. So taking the natural log doesn't fix any indeterminacy problem. This is still 0 times infinity. Okay, and so let's think about how we deal with that. So we have 0 times infinity. Well, we can do the same trick that we did with the sine example, not the previous example, but the third one that we did. Well, I'm going to write this as the natural log of x over 1 over x. And the advantage here is that now this is indeterminate in the form that L'Hopital's rule will help us, right? Which is important. So if we have x going to 0 from the right, natural log goes to negative infinity because we remember what the natural log looks like, right? So the natural log curve is going to look like that. So as x approaches 0 from the right, our y values shoot off to negative infinity. And 1 over x is going to go to positive infinity. So here we have negative infinity over positive infinity. So that means that we have infinity over infinity. L'Hopital's rule applies. Everything is fine. So we're going to take the derivative of the top. That's 1 over x, divided by the derivative of the bottom, which is negative 1 over x squared. And if we just kind of blindly apply the rules again, we would get infinity over negative infinity. We could apply L'Hopital's rule again, but this problem gets worse, right? The next step, if you apply L'Hopital's rule again, L'Hopital's rule is legal to apply again, but not helpful. So we're allowed to do it. So we'll get -1/x² all over 2/x³. We get -infinity over infinity, and we can keep doing this as many times as we like. But what we have to do is we have to take a step back and realize that that's not going to help us. Okay, so while this is true, it's not helpful. And so what we can do, though, is algebraically simplify. And instead of dividing by -1/x, I'm going to multiply by the reciprocal, right? Just a little algebra simplification. So we're going to get 1/x times -x² over 1. And of course, that simplifies to -x, which as x approaches 0 is 0. And it's not that our limit L is 0. That was the natural log of L. Okay, so the natural log of L was 0. And therefore, what does L have to be if the natural log of L is 0? So in other words, what's the value that you have to plug into the natural log to get 0? That's 1. And so our limit was 1. And therefore, we have that the limit as x approaches 0 of x to the x is 1. Okay, and so that's how we do that. This trick is very, very helpful for evaluating limits where you have 0 to the 0 or 1 to the infinity or infinity to the 0, something like that. Okay, so this trick is very helpful. So we'll do this over and over again. All right, that's enough for now.